Alright, hi everybody. We are going to be spending some time talking about how Newton's law of gravity plus circular motion can give us all kinds of great information about the motion of satellites. So in doing this, let's sketch out and think very quickly about the generic system where you've got, let's say, a star. We can call it the mass of the sun. We'll call it the sun. And then there's some planet out here orbiting. We'll do it as a circular orbit. It turns out that, so this planet, mass of the planet out here, it works with ellipses as well, of course, but we're going to stick with circular motion right now. Now this circular path has a radius of little r, we'll call it, and there is a force on this planet. That's the force of gravity. That is what is providing the centripetal force to keep this thing moving in a circle. So let's think about this in terms of circular motion. In circular motion, we learned that the centripetal force is providing the providing the force to make this mass stay moving in a circle. And we can do that as F sub c equals m times a sub c, where in this case we now know what is providing that centripetal force. It is the force of gravity, right? So let's use Newton's expression for universal gravity, and in this case gmm over r squared. Well, what are the two masses? The mass of the sun and the mass of the planet over r squared, where r is this distance for this orbital path. That has to equal the mass. Well, which mass? Well, the planet is the rock on the end of the string in this case, so we have to write this as the mass of the planet times v squared over r. We can use that expression for acceleration right now. That's pretty handy. So where can we go from here? Well, a few things can happen. We notice that, well, the mass of the planet's on both sides of the equation, so that falls away. We also notice that, okay, I've got r on both sides, so if I multiply both sides by r, this r goes away, and this to the power of 2 goes away, so it's just r down here. So let's do one more substitution for v. Let's substitute where v equals 2 pi r over t. And we've done this once before. Sorry, I guess that should be a lowercase r. We've done this before. We've seen some formulas derived this way. What do we get when we do that? Well, the left-hand side now is reduced to g times m sub s over little r, and that's got to equal v squared. That's the only thing still alive over there, which is 2 pi r over t, quantity squared, which is 4 pi squared r squared over t squared. Now I'm going to do one more very strange thing. I'm not going to solve for any particular variable in here. I'm going to solve for a ratio of t squared over r cubed. Why on earth would I do that? Well, the reason I would do that is that Kepler's third law said that t squared over r cubed for any object in orbit around a third object or second object is going to be equal to a constant. This has got to be equal to a constant. That's what Kepler's law said, and over here is the graph that summarizes a lot of his work. The constant in this case is referring to the slope of this graph, or the way they wrote it. Really, it's 1 over the slope, but that's fine. We see a straight line. So apparently there's this proportional relationship between, and they call the cube of the semi-major axis, so that's a cubed, but we're using r, that's fine. And then t squared, there's a relationship. That's what he said, but he didn't really have any reason for it. Well, what Newton said here is that, well, if I solve this equation for t squared over r cubed, I get 4 pi squared over g times the mass of the sun. And what you notice is that everything over here is a constant. So, lo and behold, where Kepler was just measuring a random constant for our solar system, it turns out to be about 3, Newton figured out, wait a minute, this constant is linked to all of these constants of the universe, basically, in the sense that 4 pi squared and capital G gives you the strength of gravity, and then the mass of whatever you're orbiting. So this is hugely more powerful than what Kepler had. This is Newton's version of Kepler's third law, and we'll find that it is incredibly important and very valuable. So Newton took it to a whole new level that Kepler wasn't able to achieve initially. Now let's see what we can do thinking in terms of circular motion and and the force of gravity, and figure out about a more generic situation. Let's imagine, okay, we have some central mass we can call that M2. And then this other mass, M1, is orbiting M2. Maybe this is a moon going around a planet. Maybe this is a planet going around a star. Whatever it is, we can make this very generic here and realize that these orbital problems can apply to anything. What we think of as just a satellite orbiting something else. So let's start back up at the beginning here. Let me switch colors just to make it a little more interesting. Force of gravity is m, well, the mass of this satellite in orbit, times v squared over r. Right? That's what we were saying because it's circular motion. And we have an expression for the force of gravity. G m1 m2 over r squared equals m v squared over r. Boy, I hope that feels familiar to you because we were just doing that. But instead of going in the direction I did before, I'm going to solve for v. So m1 goes away. Turns out the mass of the satellite doesn't matter. And if I solve for v, I get square root of g times m2 over r. This is a great little formula. It tells us the velocity of a satellite. The velocity required for the satellite to stay in orbit. And if you notice here, m2 means the thing you're orbiting. Maybe that's the Earth, maybe that's the Sun, whatever it is. All you need to know is how far away you are, the mass of that central object, and big G, the strength of gravity. That tells you the velocity of the satellite. Satellites move very, very, very fast. The ones we think of in terms of the ones that are, handle your satellite radio or GPS satellites and that kind of a thing, they have to move very, very fast. That's why they need large rockets to get them up to these speeds. But we're talking, on the order of 16,000 miles per hour or more. So even greater than that number. So that's one interesting conclusion that we can draw from this. Let's do this one more step here. I'm going to make this my starting point. Save us a little work here. What else can I figure out using some of these relationships that Newton brought out? Well, if I solve this now instead of this weird ratio, let me try to solve it for t. Okay, so the first step of that is multiply both sides by r cubed. So I get 4 pi squared r cubed over g. Now we were calling it the mass of the sun there. We called it m2 here, so I'm going to call it m2 just so we're using the same diagram. And then let me take the square root of both sides. So on the left I get t, and then on the right, well, the square root of 4 pi squared is 2 pi, and the square root of all that other stuff, that pretty much we can just keep under the square root sign there. So r cubed over g times m2, or you can just write m if you like for the central mass. This is telling us how long it takes this satellite to go all the way around one loop. This is the period of a satellite. And we saw this in class. If you don't kick your satellite hard enough, you don't get it going fast enough, it's not going to stay in this circular path. It's going to fall in and maybe even crash into the planet. If you kick it too hard, it's going to fling out of this circular path. So these are the requirements to make this work. It turns out for a lot of satellites that we use that are in low Earth orbit, this period is shockingly short, about an hour and a half. 1.5 hours it takes to go all the way around the world, which is pretty incredible. So these things are booking, they're moving. Okay, so now there's one last thing that is a unique result we can talk about, and it really makes us just think a little bit more about gravity. It's less about satellites but more about how gravity works. If I look at, again, the force of gravity is equal to mass times centripetal acceleration, because it's my centripetal force. But I also realize that for some object that's just falling in a gravity field, guess what? Well, it is experiencing a force that is equal to its mass times its acceleration. And on the surface of Earth, we would usually write that as little g, right? So I would probably write this as m times little g. But what if this isn't Earth? What if this is a different planet altogether? Or what if we are dealing with we are really far off the surface of the Earth? It turns out little g equaling 9.8 meters per second squared only works when you're very close to the surface of the Earth. It will vary because gravity varies as you leave the Earth. So let's see what we can do with that. So over here, my force of gravity is g. We were calling it m1 and m2. where m1, I guess, is this thing that's falling towards the Earth here, over r squared equals m1g, and m1 goes away, and what we can do here is solve for little g. So little g is going to be equal to big G times, we're calling it m2, you can think of it as the mass of the Earth or the mass of the planet, over r squared, how far away you are. This tells you what your acceleration due to gravity is for different planets with different masses, for varying distances off the surface of the Earth or another planet. This is huge. You know, this is how you can figure out if you drop the mass of the moon in here and the radius of the moon, then what you'll find is that this gives you the acceleration due to gravity on the moon. If I look for g where I'm dealing with the mass of the Earth over the radius of the Earth squared, and I put those numbers in, I will get 9.8 meters per second squared. So another very, very powerful result of how all of this can tie together, and we can learn some really interesting things about gravity.